Okay, let's do an example. This is problem 3.26 from the book. And in this problem, you've got a sphere that has, in this case, it's not a shell. It's a solid sphere that's defined by this potential, which depends on both r and theta. And the goal is to find v for points on the z-axis far from the sphere. So we can use our multipole expansion and maybe just look at the first couple of terms, which will give us a good approximation of the potential far from the sphere. So just drawing a little coordinate system here, we are going to try to find the potential P, but P is going to be far away, which is not so reasonable to draw on this picture. Okay, so what's our plan? Start calculating our multipole terms until we find the first few that are not zero, okay? And if we add those together, that will give us a good approximation of the potential. Okay, so let's go ahead and start by calculating the monopole term. If you guys remember the monopole term, it just depends on the total charge of the sphere. Okay, so it looks like 1 over 4 pi epsilon naught times q total over r. So we need to calculate what q total is. We can do that by calculating the volume integral of our charge density. Okay, so we want to take 2 pi to 0, pi to 0, r to 0, what we were given for our charge density, which is 1 over k. Let's see. Need some constants there. We've got k big R, rather, times 1 over r squared times r minus 2r sine of theta r squared sine squared dr d theta d phi. That needs a prime, that needs a prime, that needs a prime. Okay. So when I evaluate that integral, I can pull out the k and the r because those are just constants. I end up getting 2 pi to 0 of this guy and pi to 0 of a, this should be a prime too, of a sine squared of the theta. And then the last little bit is all the stuff that depends on r. So I'm left with r minus 2r dr, okay? And that, by the way, screwing up my primes here, all of these things should have primes. That occurs because I'm going to divide everything by 1 over r prime squared, and I got an r prime squared over here. So I'm just left with this guy here. Okay, in this case, if I just look at this part of the integral here, I'm going to end up getting r. I'm going to end up getting r times r minus r squared, evaluated at r and 0. Okay, I think if you guys notice, if I plug in r for that, I'm going to get 0. So because of that, this whole thing is going to end up being 0. Again, I could have evaluated these guys too. It wouldn't have hurt me, but I know this guy is going to give me 0. So the whole thing is going to equal 0. So I know that the total charge is equal to 0. So my monopole term is also 0. Okay, so I can skip it and I need to go to the next one. All right, let's do our dipole term. Okay, the dipole term looks something like, from the book, I can write that as 1 over 4 pi epsilon naught, 1 over r squared, and then I can take r hat times my r prime vector rho times d tau. Okay, and this should be a dot, sorry. Okay, for the way that I've got this problem set up, this is the volume integral, I'm going to take that r hat dotted with the r prime vector and pull that into the integral here. And I'm just going to evaluate this part for now. Okay, and then I can multiply it by the rest. So this is looking at the dipole moment by itself first. Okay, this little bit right here, this dot product, the way that I have my coordinate system lined up, r hat is in the z hat direction. So this is going to be equal to r prime times the cosine of theta. Okay, so that's the magnitude of the r hat. This is the magnitude of the r hat vector. This is the magnitude of the r prime vector times the cosine of the angle between them. And that's how the dot product always works. Okay, so that means that, let me scooch this around. I can rewrite my volume integral here as r prime cosine theta rho r prime d tau. All right, now I want to plug in what I have for my rho, and I'm going to pull out those constants k and r. Go ahead and put in our integration limits, pi and 0, r to 0, and then I get r cosine of theta, and that was 1 over r squared times big R minus 2r times the sine of theta, and then I still get r prime squared. All these need to be primes. I keep forgetting the primes. Okay, sine prime dr prime d theta prime d phi prime. Okay, so that's kind of a nasty looking integral. We can simplify it a little bit. Okay, we get kr out front, and then this guy is just 2 pi to 0 d phi. I can evaluate that middle bit. Let me rewrite what that ends up looking like. Pi over 0 sine squared theta prime times the cosine theta prime d theta prime, and then you get r to 0, r times r minus 2r squared dr. In this case, I'm going to evaluate that guy. Okay, if I evaluate that guy, then I end up getting sine to the third of theta prime divided by 3. And if I evaluate that from pi to 0, I end up getting 0 yet again. Okay, this is why it's kind of nice to use Mathematica, because then you don't end up doing a lot of these integrals painfully by hand, only to find out that they're 0. Okay, so the last little bit would be to do the quadrupole moment. Okay, in this case, our potential would be equal to 1 over 4 pi epsilon naught 1 over r to the third, okay, times a big old integral r, but now we've got r prime squared, and we can put in our Legendre polynomial times rho to times d tau. All right, if I plug everything in for that, I get k times r over 2. Integration limits, you get r squared 3 cosine squared minus 1, and then 1 over, you got to plug in what rho is, r minus 2r sine theta r squared sine theta dr d theta d phi. Okay, So let's go ahead and split that integral up into things that we can evaluate. Again, we still have no phi dependence, which makes that part nice and easy. Okay, this guy, we're going to pull all the terms that have theta in it. So you end up getting 3 cosine squared theta prime minus 1 times the sine squared of theta prime d theta, and then you get r to 0, r times r squared minus 2r to the third dr. Okay, you can plug all of that in, do it by hand, whatever you want to do, but you end up getting k over r divided by 2 times 2 pi times negative pi over 8 k times r to the fourth divided by 3 times minus r to the fourth divided by 2. Okay, and that's all equal to k pi squared r to the fifth divided by 48. Okay, so if I wanted to approximate the potential, I can do it just using that first non-zero term, okay, which would be the quadrupole term. So for a point on the z-axis far from the sphere, okay, remember all of those terms that are bigger than the quadrupole term or a higher order are going to be even smaller. So as long as I'm far from the sphere, then the potential is going to look a lot like just that first non-zero term, which is the quadrupole term, okay, which I can write as 1 over z to the third, since z is my r distance now, times all that other good stuff, k pi squared r, big R to the fifth, divided by 48, okay. So this stuff right here would be known as the quadrupole moment. Oh, and I forgot the 1 for pi epsilon naught. All right, hopefully that's helpful. Again, those integrals are a little bit painful. The quickest way to do them, you should know how to do them by hand, but it's always nice just to plug them in Mathematica if you can figure out how to do that quickly.